Welcome, ladies and gentlemen, to this video lecture. So we are busy proving this statement of the fundamental theorem of calculus. So it says for every c, f is differentiable at c and its derivative is equal to little f. Okay, and we wrote out a proof outline. So now we can fill out the proof. So of course we assume, that's part of our statement, assume that little f is continuous on AB, and we fix any c in the open interval AB, because the statement we want to prove is that for any c, for every c, capital F is differentiable and its derivative is that. And we have discussed how to exactly what the statement is that we need to prove and how we can split this statement up into two cases, the left limit and the right limit. Okay, so fix any c. Before we do that, let us consider the expression that we are interested in. So if h is positive, then consider the following. So we are interested in the expression f c plus h minus f of c over h minus little f of c. Okay, so let us just write out the definition of capital F. That is defined as the integral from a to c plus h of little f t dt minus integral from a to c of little f t dt all over h minus f of c. Okay, I'm going to write it this way, 1 over h, and now we see here this expression becomes, here we integrate from a to c plus h, here we integrate from a to c, so this becomes the integral from c to c plus h of f of t dt. And if I factor out this h here, if I write it this way, h of f of c, we see if we multiply this 1 over h in there, h's cancel and we're left with that f of c there. But now I'm going to write this f of c in a different way. So I'm going to write it as follows. This is the integral from c to c plus h of f of t dt minus the integral from c to c plus h of f of c dt. And why does that work? We see we are integrating this constant. This f of c does not depend on t, so this is essentially a constant. So we can in fact take it out like so, and if we then we have the integral of 1, which is just the area of the rectangle with height 1 and with width h, which is h. So this then becomes the integral of f of c. And we can put these integrals together. So this then becomes c plus h of f of t minus f of c dt. Okay, and this expression that we have here, f of t minus f of c, that comes up in the definition of continuity of f, of little f, and we will see how we can use that. So here we have fixed any c, and we have transformed this expression that we are interested in into this expression. Okay, let us continue. So fix any epsilon greater than 0. And let us define epsilon 1 as epsilon over 2. And now I'm going to take this epsilon over 2, which is positive, and now I'm going to buy a delta from the shop here, since f is continuous. So I'm going to take this epsilon over 2, which I've called epsilon 1, and I'm going to buy a delta. So since little f is continuous, there exists, so now I'm just expanding the meaning of the word continuous. There exists a delta greater than 0, so that if t is within a delta distance of c, then f of t minus f of c is within an epsilon 1 distance, which is epsilon over 2. So here we have used the assumption that f is continuous, that little f is continuous. Okay, and we have now found some delta. So there exists some delta. Good. So now we will use this delta to show that if h is greater than 0 but less than this delta, then everything works. So remember, here in our outline we had to somehow construct this delta. In fact, I'm going to call, I'm going to keep that delta there. I'm going to call this delta something different. So let's call it delta 1. There exists a delta 1, so that if this expression is less than delta 1, then this expression is less than epsilon over 2. And just to keep the symmetry between our plan or our outline, I'm going to define delta as exactly delta 1. So here we see us filling in this part from our proof outline. And now notice here our proof outline already tells us what we have to do next. We have to assume that h is bigger than 0. H is bigger than 0 but less than delta. And delta we have defined to be delta 1. Okay, so now notice for all t in the interval from c to c plus h, so all t in this interval that we're integrating over from c to c plus h, we can say something. What can we say? We see that if t is in this closed interval, it is of course less than c plus h, and it is greater than c, but c is greater than c minus h, and t is less than c plus h. And if we subtract c's, we see the following: c minus h. So t minus c is less than or equal to h, but h we have assumed to be less than delta. So notice for all of these t's we have the following. So this expression is less than delta, and lo and behold, if this expression is less than delta 1, then we get something for free. We get that this expression is less than epsilon over 2. And that is what we will use. So therefore we have, so since delta is equal to delta 1, and now we have satisfied this condition, we get this for free. So therefore we have f of t minus f of c is less than epsilon 1, and epsilon 1 we define to be epsilon over 2. And now, so let's rewrite this a little bit. F of t minus f of c, that is less than epsilon over 2, greater than epsilon over 2, minus epsilon over 2. And now, by theorem A.1.10 number 2. So what does that theorem say? That theorem says that the integral is monotone. So I'm just going to put that in brackets. The integral is monotone. So if you take the integral, it preserves the inequalities. So if you take the integral everywhere here, it preserves the inequalities, but the inequalities turn into less than or equal to. So what we obtain is this holds for all values t in this interval from c to c plus h. So if we take the integral from c to c plus h, what do we get? We get minus epsilon over 2. It's less than or equal to, actually let's put our what variable are we integrating over? dt, less than or equal to the integral of c to c plus h of f of t minus f of c dt, less than or equal to integral from c to c plus h epsilon over 2 dt. Okay, but what we have here on the left and on the right are just constants. So constants integrated over c to c plus h. So what is the area of these rectangles with width h? Over here we get minus epsilon over 2 times h is less than or equal to integral from c to c plus h f of t minus f of c dt, less than or equal to h times epsilon over 2. Okay, and now we're almost there. Okay, let us divide everything by h. Remember, h is positive. We assumed h to be positive, so dividing everywhere are the direction of our inequalities don't flip, and h is strictly positive, so we're not dividing by 0. So this is less than or equal to h, integral from c to c plus h, ft minus fc. That's a t minus fc dt, less than or equal to epsilon over 2. So all we did there was divide everywhere by h. Okay, but now we see this expression is between minus epsilon over 2 and plus epsilon over 2. So the absolute value is less than epsilon over 2. So the absolute value of 1 over h c plus h is equal to f of t minus f of c dt, and that is less than or equal to epsilon over 2, which is less than epsilon. But we have seen that this expression, where did we do that? Where did we do that? Here. We saw this expression is exactly this expression that we are looking for. So but we have that f of c plus h minus f of c over h minus f of c. This is equal to this expression that we have here, 1 over h c plus h f of t minus f of c dt, which is less than or equal to epsilon over 2, which is less than epsilon. So we have proven that the right limit as h goes to 0 of f of c plus h minus f of c is over h is equal to little f of c. So, and this concludes R. This statement R that we wanted to prove. Okay. So I will leave the left statement, so the statement as h tends to 0 from the left, that I will leave as an exercise. That is not particularly difficult if we have seen the one for the right limit. And now what we should notice is, so since f is differentiable on AB. So remember here when we wrote out our proof, we assumed, or we fixed any C. So this proof works for any C. So let's add here to our proof. We have now proven for any C in our open interval. We have proven that this limit exists and is equal to little f of c. And since f is differentiable on the open interval AB, it is also continuous. So f is continuous on AB. Now remember, differentiability implies continuity. Continuity does not necessarily imply differentiability. That is a common mistake that happens if you are not paying attention. So differentiability implies continuity, not the other way around. Okay, so we automatically, by showing that capital F is differentiable, we automatically get continuity. And then if you remember the statement of the fundamental theorem of calculus, all that remains, so we have now proven 1/2 of this, all that remains is to show that capital F is continuous at the endpoints of the closed interval A, B. So continuous at A, continuous at B. And that we will also leave as an exercise. So exercise, show that capital F is continuous at A and at B. Okay, and if once we have filled in those details, we will have a complete proof of the fundamental theorem of calculus. Okay, so in the coming video lectures we will look at a couple of consequences of the fundamental theorem of calculus. I will see you in the next ones.